All right, section 3, we're going to learn another theorem that's going to help us to find these real zeros of polynomial functions. And this one is called the factor theorem. The factor theorem says this. It says x minus r is a factor of f of x. So some x minus some r is a factor of f of x if f of r equals 0. So this is an offshoot of the remainder theorem, because remember in the remainder theorem, if we plugged this root in and got a number, that was the remainder. So simply what the factor theorem is saying is when you divide a factor by f of x, its remainder is going to be 0. So we can look at a couple different ways to do this. Here we have two factors. We want to check if they are factors of this other polynomial. So this is our function, 2x to the 4th plus 7x cubed minus 4x plus 15. So one way is to use this factor theorem, which says, okay, let's just go ahead and call this f of x. So if in this case, if f of 2 equals 0, it's a factor, and if it's not 0, it's not a factor. And again, we're just using 2 because that's the number x minus the root. So if we plug that in, we get 2 to the 4th plus 7 times 2 to the 3rd minus 4 times 2 plus 15. So calculating all this, I get 95. And really we don't care what we get. The big thing is that we don't get 0. So what that's going to tell us is x minus 2 is not a factor of f of x. And the same way you could say is 2 is not a 0 of f of x. So these are basically saying the same thing. Not a factor, and 2 is not a real 0. So let's look at this one. We have x plus 3. So in this case, we could do the factor theorem again, where we plug in negative 3. Or in this case, if I want, I can divide out. I could do the synthetic division, negative 3, 2, 7, 0, because there's no x squared, minus 4, and 15. And remember, our remainder will be in this last spot. So if you want, you can just divide it. If you didn't want to use the theorem, that works fine too. So 2, negative 3 times 2 is negative 6. 7 and negative 6 is 1. Negative 3 and 1 is negative 3. Add those, you get negative 3. Add those, you get 9. Negative 4 and 9 is 5. Negative 15, which gives us 0. So this is the remainder. The remainder is 0. And I would have got the same thing. Now I know if I would have plugged in negative 3 to the function, I would have got 0 as well. So what that's telling me is it's telling me we have a factor. It's telling me x plus 3 is a factor. Now there are obviously probably other factors, but this is definitely one of those factors. The last theorem we're going to talk about is the rational roots theorem. The rational roots theorem is a way to try to figure out what the rational roots of a polynomial are. Now remember what a rational number is. A rational number is essentially anything that can be written as a fraction. So for example, 1/3 is a rational root, but pi is not a rational root because you can't write it as a fraction. Negative 3 is a rational root because it can be divided by 1. But say the square root of 2 is not a rational root. So we're going to try to figure out where we can find rational roots for a given polynomial. Okay, and that brings us to this rational roots theorem. So the rational roots theorem says this. If we're given a polynomial function, and we'll call it f of x, just for generic sake, and we'll say f of x is equal to a x to the n plus a to the n minus 1 x to the n minus 1 plus, we'll call it a0 down here. So the big thing is you have a highest power, we'll call it n in this case. There is a number in front of it, and that number is a. And then there is a constant number at the end, and that number we call a0. So if we're given a polynomial that looks like this, we say all possible rational roots have to be in the form of p over q. And the question is, what is p and what is q? So p is going to be factors of a0. So it's basically factors of this last number. And q is going to be factors of a, which is the first number. Now again, this only gives possible rational zeros. Not all the ones we find are going to actually be zeros. They're actually not going to be plugged in and find the number 0. But these are the only ones that are possible rational solutions. Any other rational we can exclude. So if we look at this first example, where we have 2x cubed plus 11x minus 7x minus 6, our factors of p are going to come from the 6. And what multiplies to 6? It's 1 and 6, 2 and 3. That's all it multiplies to give us 6. Now our q's are the first number, and that's simply 1 and 2. So the possible rational roots, the only rational numbers, the only numbers that can be written as a fraction that could be zeros of this, would simply be all the p's divided by all the q's. So I'll take all these numbers and I'll divide it by 1 first. So that's 1, 6, 2, and 3. And then I'll take all the same number of p's and I'll divide them by 2. So we have 1 over 2, which is 1/2. We have 6 over 2, which is 3, but I already have 3, so I don't need to write that again. 2 over 2, which is 1, which I already have, so I don't have to write that one again. And 3 over 2, which I don't have, so that's another possible. So of all the fractions, of all the rational numbers that there are, which are infinitely many, we essentially can pare it down to only 12 of them that could even possibly work as rational zeros, and they're in this list. Now the second question says, well, okay, well, what if they are, which of these are going to work? There's 12 of them. Which of these are going to be rational zeros, if any? So one idea is you can basically plug in. The first idea is we can plug in each one and see which of them make the function equal to 0. Okay, that's a lot of work. That's 12 numbers to plug into the function. So that's kind of a thing that typically we don't do. We used to do, but now that we have some technology, we do it a little different way. Because with the graph, if you remember from chapter 1, zeros always occurred at x-intercepts. So if we look for x-intercepts, and we just have to look at these 12 numbers, those would find the values for our function that are 0. So let's go and look at a couple examples. This first one says, if x plus 1 is a factor of f of x equal x cubed minus 7x minus 6, find the other zeros of f of x and write it in factored form. Verify your answer with the graph of f of x. Well, we know one factor is x plus 1. So if we remember our consequences of zeros, there's lots of things that means. But the easiest way to remember is remember that f of x would have to divide by x minus r. Okay, the remainder is 0, so it divides. So what I'm going to do is I'm going to divide x plus 1 by x cubed minus 7x minus 6. I'm going to do that synthetically. So negative 1 is my 0. 1, 0, negative 7, negative 6. Notice I put the 0 for the x squared. Bring the 1 down. Negative 1 times 1 is negative 1. 0 and negative 1 is negative 1. Negative 1 times negative 1 is 1. Negative 7 plus 1 is negative 6. Negative 1 times negative 6 is 6. Remainder of 0. Not surprising. So if I'm thinking about f of x, well, I just divided this one factor, and then remember from our synthetic division, this is my remaining polynomial. So this is x squared minus 1x minus 6. Because recall, when you divide, always one less. So now I can rewrite my polynomial. I know my polynomial is now x plus 1 times x squared minus x minus 6. So now all I want to do is I want to try to factor the remaining quadratic. If not, if it's not factorable, we'll eventually use quadratic formula and things like that. But if we can factor this, we can find our other zeros. And this one's a really easy one to factor. It's x minus 3, x plus 2. Two numbers that multiply to negative 6, add to negative 1. That's our f of x. So now that we have it in factored form, we divided out the one we knew. We got this remaining one. We know our zeros from each factor. Because remember, if we have a factor, it's just the opposite one for the zeros. So it's negative 1, it's positive 3, and negative 2. So if you want to verify this with your graph, go ahead and graph this in your graphing utility, and you'll find, I will guarantee that it crosses at these 3 spots. Because those are our zeros, so that's where it has to have an x-intercept. All real zeros have to have an x-intercept at those spots. So look at our last one. The last one says factor x to the 4th minus 7x cubed minus 22x plus 28x plus 72 by finding all the zeros. Well, unfortunately, like the last one, this one does not give us one to start with. It just says here's the polynomial. So generally what we'll do is we'll first start by finding the possible rational zeros. What are our possible zeros for this function? And remember, that's going to be factors of this number divided by factors of the number there. Well, the first number is 1, so really all I'm looking for is factors of 72, which are 1 and 72, 2 and 36, 3 and 24, 4 and 18, plus or minus for all these. We have 6 and 12. Still multiplies to 72. 8 and 9, and I believe that's all. So when we're trying to figure out, all we have to do is plug in these numbers, but there'd be a lot. This would be 24 numbers because you have the positive and the negative. You'd have to plug into the function and see which ones work. So that's not very efficient. So what we're going to do is we're going to use our graph to try to see if we can figure out which of these work. Best case scenario, we find lots of them. We know it's degree 4, so there should be 4 factors. So hopefully we find them all. If not, we'll have to see what else we can do. So when I graph it, hopefully you can pause the video and graph it yourself. I found only 3 zeros, interestingly enough. The 3 places I saw that had zeros were negative 2, positive 2, and positive 9. Which, good news, were all on my list, so that's good. So I have 3 factors. I know x plus 2, I know x minus 2, and I know x minus 9. But unfortunately, I don't know anything else. So what we'll try to do is to find any other remaining zeros. Just like we did above, we'll divide out the ones we know. So we know 3 of them. So instead of dividing once like we did above, we'll have to divide 3 times. So we'll take -2, which is the first one, and then I'll take my polynomial 1, -7, -22, 28, and 72, and I'll synthetically divide. Now, if I've done it right, 0 should be the remainder. So I'll bring down the 1, -2 times 1 is -2, -9, 18, -4, 8, 36, -72, and there is my 0. So it started at degree 4, so if I divide it out once, this is a degree 3 polynomial, but I still have 2 other zeros that I haven't done. So the idea is, now that we have essentially divided it once, I'll ignore this remainder and I'll take these remaining 4 numbers and I'll divide it by the next 0, because it's some polynomial that's left over after I divided 1, so I can divide another 0 out. So that's 1, 2, -7, -14, -18, and that gives me -36, and again, another remainder of 0. So I divided out the -2 and the 2. So now all that's left is to divide out the 9. So I'll have 1, 9, 2, 18, and 0. So now this is going to basically be my last factor, because remember, this divided once made me a third power. I divided out again a second power, so this should just be a first power. So this is 1x plus 2. Now, interesting enough, if you look at our factors, we already had x plus 2, but it is actually okay to have 2 of the same factors. So in this case, our last factor is x plus 2. So our zeros are going to be -2, 2, and 9, and then for this last one, we have another x plus 2, so we say it's -2 again. So in a list of zeros, it's actually okay to have 2 of the same number as a 0. We call this a multiplicity. So hopefully this was helpful. Let me know if you have questions on how to find some of these zeros.